Hello everyone, my name is Jonathan Galena and I'm going to be talking to you about page tables. So today I'm going to be talking to you about what page tables are and what they allow us to do. Then I'm going to be going over an example of how to calculate a logical to physical address translation. Then I'm going to talk about the translation lookaside buffer and a little bit about page replacement algorithms. So what are page tables? Basically, page tables are a mechanism that allow us to run multiple processes more efficiently. It does this by eliminating external fragmentation. Looking at this picture to the left, these holes in memory between the processes are what is known as external fragmentation. Page tables also allow us to not have the restriction of contiguously allocating memory to a process. In the picture, let's say that these external fragmentation holes are the total amount of the memory to these external fragmentation holes are enough for process 7 to fit. However, the allocated memory will not be next to each other, or the memory will not be contiguous. Page tables basically say that this non-contiguous allocation of memory is okay. So how do page tables work? Each individual process is given a private memory and address space. These private addresses are called logical addresses. There is a mapping of logical to physical addresses stored in what is known as the page table in RAM. The Memory Management Unit, or MMU, of the CPU looks at this page table in RAM for the physical address to look for it in memory. With page tables, physical memory is broken up into pages and frames. When a process requests something with a logical address, the MMU figures out where it is in physical memory and returns the data found at the physical address to the process. So let's go over an example of how this is calculated with the example shown on the screen currently.
Alright everyone, so I'm just going to walk through this quick example real quick. Our address, which is a 32-bit address, is 0x9117758B in hex. Our frame for this particular example, we're just going to say is 68 hex. We're going to be handling a one-level page table, which is 20 bits. And we're going to be trying to find the lowest and highest address of this particular frame, and then we're going to be actually finding the logical to physical address translation. So because we're handling a one-level page table, we know that this address is going to be split up into two parts. The first part is going to be the page number, and the second part is going to be the offset. So because our page table is 20 bits, we know that 20 bits equals to 5 hex digits. So our first 5 hex digits of this address is going to be the page table. So our page number. So our page number is going to be 0x91175. There it is. Alright, so then the remainder of the address is going to be our offset, which is going to be 12 bits or 3 hex digits. And we know that the offset is going to be 12 bits because 32 bits of our address subtract from 20 bits from our page number is going to be 12 bits. So our offset is going to be 0x58b. Now, in order to find the lowest address of the frame, we're going to need to find the page size. And our page size is simply a fixed size of the power of 2. So our page size is going to be 2 to the number of bits of our offset, or 2 to the 12th, which is 0x1000 in hex. So in order to find our lowest address of the frame, we're just simply going to multiply the frame with the page size. So hex multiplication of 1000 times 68 will be 68,000 in hex. That's one problem done. We have our lowest address of the frame. In order to find the highest, all we do is simply add the page size to our lowest address, and then we're going to subtract 1 because, as we know, computers, we like to go from 0 to n-1 rather than 1 to n. So it'll be 0x68,000 plus 0x1000 subtract 1, which will be, of course, 68FFF. And of course, this will be 32 bits, so we'll just pad the extra zeros in front of it, so it'll be 000 68,000 000 68FFF. Now, in order to do the translation, all that's simply needed to do is take the lowest address, add it to our offset, and we'll have 68,000 plus 58B hex, and we'll have 6858B. All right, so what does this all mean in the grand scheme of things? So branching off the example that we just did, our process is requesting data from its logical memory at logical address 9117758B. However, in reality, the CPU is going to take that logical address and give it to its MMU, where the MMU will go to RAM, look at the page table, and get the physical address translation. With the physical address, it's going to look at that address in physical memory and return the data there. So with physical memory, it's going to be broken up into 100,000 frames. And we know that because our page table or our page level is 20 bits, or 100,000 in hex. Within each of those frames, it has 1,000 entries. And we know that because we just found the page size to be 2 to the 12th, or 1,000 in hex. So with this physical address, the CPU is going to be looking at frame 68 at entry 58B. Once at frame 68, entry 58B, it's going to return, or it's going to grab the data and forward it back to the process. And the process can continue doing whatever it's doing now that it has the data that it just requested. However, one thing to note is that the process has no idea this has all happened. All of this paging, this memory access, it has no idea that it happened. What it thinks is that the CPU took its logical address, which should be the physical address, and went to physical memory at that address and returned the data, not going through all of this paging sequencing.
There is a problem to using page tables, however. The page table is in RAM. In order for the MMU to translate the address, it needs to perform a lookup, which in turn needs a memory access. This results in 2 memory accesses, which is very slow and very inefficient. The solution to this problem is to use what is known as the translation lookaside buffer, also known as the address translation cache. The TLB is found in the CPU and is fast but also expensive. Because it is so expensive, there are limited mappings that the TLB can hold. But before we get into that, let me explain how the TLB fits into all of this.
Alright, so let's go back to this diagram now that we've added the translation lookaside buffer to the CPU. So the steps are pretty much the same, beginning and end. The process is going to request data from logical address 9117758B. The CPU is going to take that logical address, but before the MMU goes to the page table in RAM, it's going to first look at the TLB to see if the logical to physical address mapping is already there. If it is, called the TLB hit, the MMU will simply take the physical address from the TLB to the physical memory to look up and retrieve the data. However, if it is not, called a TLB miss, the MMU will have to go to RAM to look at the page table, and the process pretty much is the same as without the TLB. One thing to note is that the MMU going to the TLB is much faster than having to go to RAM to the page table. However, if it is a TLB miss, the MMU still had to go to the TLB and cost all of that time to search the entire TLB. Even though it is much faster than going to RAM, there still is that time to look up the TLB. But so actually, let's add some numbers to make this a more concrete example. All right, so now we have some example numbers here. Let's just say our TLB lookup costs 10 nanoseconds. Our data retrieval going from physical memory and retrieving the data costs 100 nanoseconds. And then our page lookup going from the MMU to RAM to look at the page table costs 100 nanoseconds. So with the TLB hit, we'll look at the TLB and we'll find it, resulting in 10 nanoseconds. Then we'll retrieve the data, resulting in 100 nanoseconds. And I add that together, we'll have 110 nanoseconds. With a miss, we'll still look at the TLB, but we won't find it, so 10 nanoseconds. We'll have to look at the page table, resulting in 100 nanoseconds. And then we'll have to actually retrieve the data, which is 100 nanoseconds. Add all those up, we'll have 210 nanoseconds. So, let's just say for a moment that we did not have the TLB lookup. We'll always have a constant 200 nanoseconds going from looking at the page table and then retrieving the data from physical memory. With the TLB, if we have a hit, we'll save 90 nanoseconds by not looking at the page table and then only looking at the TLB. With the TLB miss, we do add a 10 nanosecond from the 200 nanoseconds without the TLB, But in terms of opportunity cost, that is worth it because of the 90 nanoseconds that we save with the TLB hit. Also, I'd like to point out that we've only been working with a one-level page table. With multi-level page tables, 2, 3, and so on, we have to add another 100 nanoseconds per level. So with the TLB miss, we'll have 10 from the TLB lookup. We'll have data retrieval, 100 nanoseconds. And then we'll have level 1 or level 0 of the page table, and then level 1 of the page table as well. So we'll have an increase of 100 nanoseconds per additional level.
So how do we get the mapping saved into the TLB? On a TLB miss, a page fault is generated, which basically says that the mapping that the MMU was searching for was not found. When this happens, we either simply add the mapping into the TLB if there is room, or we will have to kick an already saved mapping out of the TLB to make room for the next one. This begs the question of how we determine what mappings should go into the TLB. There are a number of page replacement algorithms out there to determine this. I will go over one of the simplest ones, called the first in, first out algorithm.
Alright, so let's go over a quick TLB first in, first out page replacement algorithm. So let's just say that, for example, the TLB can only hold 3 mappings, and currently the TLB has no mappings. So let's say that process wants a mapping of 0. It generates a TLB miss and a page fault, so based off of that, we'll add the mapping to the TLB. So that way, if another process wants the same mapping of 0, we'll generate a TLB hit, and everything is fine. Let's say, for example, if the process now wants to have a mapping of 1, generate a miss, generate a page fault. Now we'll add 1 in. Okay, and everything is fine if 1 is requested again. And so on and so forth, we'll have 2. Now let's just say a process wants mapping 3. Generate a miss, generate a page fault. However, there is no more room in the TLB to add the mapping without replacing one of the mappings currently in the TLB. So, based off of that, we'll remove the oldest, the first in of that was added to the TLB. So replace the 0 and add in the 3. And then everything is fine if somebody wants, or if one of the processes wants another mapping of 3. So now we'll add in, say another process wants to go back and have a mapping of 0. So generate a miss because 0 is no longer within the TLB, generate a page fault. So the oldest mapping within the TLB is now 1. Replace the 1, add in the 0, and it's dying. Add a 0, and everything is fine. And the algorithm basically goes or repeats itself after that.
In conclusion, paging and page tables are a powerful mechanism useful to the operating system. Just a quick recap of what we covered. We found out what page tables are, found out how to determine a logical to physical address translation, talked about the TLB, and went over the FIFO, first in, first out page replacement algorithm. Thank you for your time.